Okay, it's time to start start doing functions. This equation right here should have been on this piece of paper, and so should the graph, but it's not, so I'm going to sketch it for you. It's a x cubed graph with a negative leading coefficient. So it comes down like this, crosses like this. Okay. I'm going to label these points. This point right here is 1.67, comma 1.63. That point is 2.186. This point is 1. This point is 0, negative 3. And this is negative negative 0.686. All right. We're going to be talking about maximum and minimums of the function. When we talk about max and mins, we're talking about the largest y value or the smallest y value. So a maximum can have an absolute or a local. Absolute means it's the biggest y value you can have. In this case, our function has arrows here. It goes to infinity. So there is no absolute maximum because there's always a number that's going to be bigger than the last one you've picked. But a local one means you have a limited domain. So if I take this graph and only look at x values between here and here, this is going to be a local maximum. When you list your local maximum, you're going to say it happens at x equals 1.67, or you give it as an ordered pair, 1.67, comma 1.63. Okay? And the difference being, if it asks you what is the maximum, you go looking for the y value. If it asks you where is the maximum, it's the x value. That's really big in calculus, not so much in pre-cal. All right? The same thing for minimum. Minimum, you're looking at smallest y value. Okay, this graph has arrows on both ways, so there's no absolute. It has a local at 0, 3, negative, 0, negative 3, or at x equals 0. Okay, an increasing function happens, excuse me, when as x is getting bigger, your y is getting bigger. State as an interval, use the x values, not the y values. So in this case, it's going to be increasing from 0 to 1.67. Okay? All right. Decreasing is when, as x goes to the right, y is getting smaller. In this case, our intervals go from negative infinity to 0 and from 1.67 to infinity. The thing to watch out for here is this is positive, and it's confusing a lot because if you go up here to the graph, the arrow's pointing down and you think it's negative infinity. But we're talking about the intervals on the x value. Sorry, me and my arm, it leans on something and then I get a mess. Okay? So pay attention to that. Let's go back to blue. Concave up, cup, down, frown. Okay? Increasing and decreasing, here, use max and mins as endpoints. concave up and down, use inflection point as endpoints. So let's talk inflection points first before we talk about concave up and down, okay? So inflection point. It's the point where concavity changes. Point where concavity changes. You need calculus to find it. So we estimate the inflection point as the midpoint of the max and min. So in this case, we would have 0 plus 1.67 divided by 2 equals 0.835. Okay, so now let's go back up here and talk about concavity. This function is concave up from here to its inflection point. Okay, so you're going to write it as negative infinity to 0.835. It's concave down from here like that. So it goes from 0.835 to infinity. You'll notice again, these are x values, no y values. We want to know the interval where it happens, okay? All right. Next, we're going to talk about odd and even functions. This is a tough concept, okay? We're not talking about the degree. Y equals x squared is a second degree equation. Y equals x cubed plus x squared minus x is a third degree. We're talking about whether the function is odd or even as its symmetry or what points fall on the graph, all right? An odd function, here's an example, is y equals x cubed. And what you have to do to check is you know that f of negative x is equal to negative f of x. Or x, y, and negative x, negative y are on the same graph. The graph. Okay? So if we try this and call this f of x equals x cubed, and you do f of 1, you get 1 cubed, which equals 1. If you plug in negative x, which is negative 1, you get negative 1 cubed, and that equals negative 1. So 1 is on the graph, and negative 1's on the graph. It's an odd function. When I ask you to prove something being an odd or even function, you have to do it algebraically. So here's my function. F of x equals x cubed minus x. And they say, prove to me that it's odd. So if I plug negative x into this function, I get negative x cubed minus a negative x. If I clean that up, you get negative x cubed plus x, and that's equal to negative f of x. If I took this and multiplied by negative 1, you'd have negative 1 times x cubed minus x. You get negative x cubed plus x. And this matches that. Okay? So therefore, this is an odd function. Okay? Even functions. Y equals x squared. And what happens is when I plug negative x into the function, I get the same answer. Or x, y is on the graph, and x negative y are on the graph. Again, you change this to f of x equals x squared. F of 1 is equal to 1 squared, which is 1. If I plug in negative x, you get negative 1 squared, and you get 1. They both equal the same thing. Likewise, if I ask you to prove a function is even, you have to do it in the generic set and just use f of x, of negative x. So here we go. I have 2 minus x to the 6th minus x to the 8th. Plug in negative x. You get 2 minus negative x to the 6th minus negative x to the 8th. Clean it up. Negative x to the 6th is positive x, so you get 2 minus x squared. This is positive. Oh, not x squared, it should be, sorry, to the 6th. All right? And again, this matches that. So plugging f of x, negative x in, it equaled what you started with. Will that always be true? No. Let's try a different one. I have f of x equals x to the 5th minus 2x to the 4th plus x minus 2. F of negative x to the 5th minus 2 times negative x to the 4th minus negative x minus 2 is negative x to the 5th minus 2x to the 4th plus x minus 2. This does not equal that. So, f of x does not equal f of negative x. So it's not even. All right? This is tough stuff. Stop it, pause it, go back, look at it, do it over again, try again. All right? Symmetry. Symmetry with respect to the x-axis. It means it's not a function. You know, if I fold it over the x-axis, will it land on top of itself? Yes, and you end up with 2 y's for the same x. So you have x and y and x and negative y on the graph, and you have 2 y's for an x, and it's not working. Okay? If it's symmetrical to the y-axis, it's also even. So x, y, and negative xy are on the graph. The first quadrant reflects in the second quadrant. So look at graph 2. Okay, this is number 1. This is number 2, number 3, number 4. If we go back to number 2, you'll notice this quadrant reflects in this quadrant. Okay? If it's symmetrical with respect to the origin, it's also odd. Origin, odd, they both start with an O. You know that x, y, and negative x, negative y are on the graph. You can rotate the first quadrant. To third quadrant. See graph number 1. Okay, so we go up here. This is the first quadrant. If I rotate it, it ends up in the second quadrant. All right? That was a lot of material. That was tough stuff. You might want to listen to the whole thing all over again, at least the even and odd stuff, because I know it's something you haven't seen before. And the last question is, does a function have to be even or odd? No. Okay, look at number 4. graph number 4. It doesn't, 1 and 2 don't reflect, 1 and 3 don't rotate. And that's all I got for you.